Hi, my name is Yuanyuan and I'm an incoming assistant professor at University of California, San Diego, the Electric and Computer Engineering Department. My research focuses on learning and control for energy systems. So a little bit about me, I did my postdoc training in the Computing and Mathematical Science Department at Caltech. Before that, I received my PhD in Electrical and Computer Engineering and my master's in Statistics and ECE, all from University of Washington, Seattle. I did my undergraduate in China from Nanjing University. I will start as an assistant professor at UCSD from July 2021. And during my PhD, I did several internships at DeepMind, JD.com, and Doosan Great Tech. So my research focused on machine learning and control for energy systems. Energy system is a complex network system. Actually, energy system has changed a lot during the recent years. First of all, we have more renewables. Renewables like solar and wind have been added into the system. And California have the goal of reaching 100% clean energy by the year of 2045. Also, energy storage has becoming a game changer in the system. Storage and electric vehicles can charge and discharge to move energy across time and space. In addition, on the demand side, instead of just consuming energy, we say like users are optimizing their behaviors. For example, large IT companies like Google and Microsoft, they're using artificial intelligence to reduce their electricity bills. So all these changes have makes the energy system more complex, more uncertain, and therefore more challenging to operate and control. For my research, I focus on designing more effective machine learning, control, and optimization algorithms in energy systems. And the core approach here is to combine our physical understanding of these devices and operational data, thus to design more efficient algorithms. And this work have been in collaborations with different industry collaborators, including Microsoft, Doosan Great Tech, Centrica Energy, JD.com, and Google DeepMind. To start with, let me give you a few examples about how we can use machine learning for energy system applications. One important application is on smart building energy management. Building accounts for 35% of the total US electricity consumption in 2019. And a large commercial user spend a lot for their electricity bills. For instance, my graduate school, University of Washington, pays over $1 million per month for its electricity bill. Therefore, for both the sustainability reasons and economics considerations, there is a strong motivation for commercial buildings to reduce their electricity consumption. So how can they do that? Nowadays, we have an increasing amount of data and buildings, ranging from indoor temperature sensors, camera to estimate the building occupancy, and outside weather data, to the smart meter data in recording the building energy usage. Our iClear 2019 work proposed a novel neural network architecture called Input Convex Neural Network, which models a relationship between various of sensor input to the building energy consumption. And furthermore, we can use the same input convex neural network to reduce the building energy consumption by finding the optimal temperature set points. So under different occupants' comfortable constraints, from a tighter constraint like 19 to 24 Celsius degree to a wider range like 18 to 26 Celsius degree, our proposed method can reduce the building energy consumption from 20 to 30%. In addition, compared to regular neural network, our method is guaranteed to find a stable and optimal temperature set point, rather than stuck in any of the local optima points. Our method is patented and deployed by Centrica Energy in real-world building systems. Another appealing example is data centers. So data centers are perhaps one of the most energy-intensive building types, and the demand for data centers has exploded over the past years due to the soaring usage of social media, remote working, video, and mobile apps. So the rapid growth of data center has also caused intensive capacity expansion burden for the grid and also lead to skyrocketing electricity bills for IT companies. So in collaboration with Microsoft, we have discovered an innovative approach in using the energy storage devices, also called the UPS devices in data center, to do both peak shaving and provide frequency regulation in data centers, which can lead to over 10% operation cost saving for data centers, and also helps the electricity grid in better handling the renewable uncertainties coming from wind and solar. So in the energy system level, with the increasing of EV, electric vehicles, and rooftop solars, the grid voltage and frequency control problem also becomes more challenging. And our recent work has explored data-driven approach for power system control to show great promise in keeping the system operation always around the nominal operation values and under unknown network topology and time-varying dynamics. So although all our works we developed start from energy system applications, it turns out some of the other methods we mentioned before can generalize well to other cyber-physical systems, such as supply chain management and robotics control. An important problem in supply chain management is the inventory management, where like both excess stock or out of stock are both undesirable. So unlike traditional two-stage inventory management method, where we first focused the future demand and future vendor delivery time, and then solve an optimization to get the order decision. Our Management Science 2021 work proposed a novel approach to do end-to-end inventory management using deep learning approach. So it has demonstrated over 10% cost reduction and is patented and adopted by JD.com, one of the largest e-commerce in China for their inventory management. Similarly, in robotics applications, our robust reinforcement learning algorithm in Europe's 2019 and iClear 2020 have shown great performance in handling the sim-to-real reinforcement learning challenge. Specifically, when we train a robotics arm in a nominal simulator, we can also ensure the land policy can generalize well, can operate safely and robustly in real-world scenarios with different arm lengths, friction, and different specifications. So as a summary, my research focused on learning and control for energy system applications and broader intelligent system scenarios, including transportation, supply chain, and robotics. And if you are interested in any of our works, feel free to check out our website for more details. And if you have any interesting ideas I'd like to discuss with you, you can email me at yyshi@eng.ucsd.edu. And thanks a lot for listening, and I'm looking forward to seeing you in the MICS research session.